firstly, lesson 24, we will be able to find the voltage drops on various circuits. The goal for today is to sort of talk about how do we go about the calculations that we use on a regular basis with regards to these circuits. So that's what we're going to be looking at. Before we get to that, let's talk about today's stolen idea. This is brought to us from Everest because I found his recently. Charles Francis Jenkins was an American inventor and engineer and was born in 1867. He moved to Indiana, and then most of his that's where he stayed when he was young. He was in college. He was in the position of a stenographer for the government. In his spare time, he visioned himself being an inventor and engineer. In 1891, Francis Jenkins tried to develop the first motion picture projector. So that's a projector. This is different from a TV, which people had in their homes. This is the first projector, so you could actually turn film into something that people could see, and also then get the whole idea of a moving image, which would be pretty cool to start off with. In making his first projector, even though the images project were too small to be viewed by a large audience. In 1985, he left his job and partnered with Thomas Armat, and the two became business partners. They improved Jenkins' initial design and called it the Fantascope. So this is now we've actually got a projector happening here. They charged 25 cents, which probably would have been a fair decent amount back then, to grab a look at the moving images. Whilst this was all good, their relationship quickly became unstable. All that's not good. Jenkins took one of the three Fantascopes to show people in his home neighborhood of the moving images. He filed for a patent of the Fantascope, and to say he sold them into the Fantascope, but this contradicted the fact that Armat had also written a patent saying they were joint owners. The U.S. Patent Office had to officially deem that both Thomas Clark were the owners of the Fantascope. Who's Thomas and Clark? Why are these guys? Enraged by this, are they their names? No, Thomas and Charles. Not Thomas Clark. Whoopsies. Blurted out Gordon whilst Charles was doing this, that Thomas negotiated with Thomas Edison about selling the Fantascope. Yeah, eventually Jenkins decided to. I think I may have cut off the end there. But the idea is that, sorry, just grab a look at that. The idea here is that you got to be careful if you're going to partner up with someone. This goes for as well with any sort of business. And one of the pieces of advice here is be careful. Try not to partner up with friends, because ultimately it has to be a business decision. People love moving in with friends and partnering with friends and stuff like that. I don't know who that. Sorry, someone's trying to join the class. I think that's one of our students, but I don't recognize it. It's it's always sometimes can be a bit hazardous because you're not really too sure whether or not your relationship's going to survive if the business falls apart. In this case, it looks like their relationship kind of got a bit faulty, and then because it's this really good invention, and of course if you sell it to Edison, that's really bad. But yeah, it's actually a really good, interesting take on this. Normally when people write, when I've seen this story, it's usually just, you know, Charles invented the projector and it was stolen by his partner. But this is actually a big difference. So it says, well, they worked on it together. So technically they both have claims to it, not just Charles Francis Jenkins. But it's up to you guys what you think about that. Let's look back now at what we did last lesson. Last lesson, what we talked about was firstly, some parts of the circuit. We said basic ideas of drawing a circuit. Use straight lines and use symbols. We talked about these symbols here and what they mean. And then we talked about how you can tell which side is the positive side of a battery and which side is the negative side of a battery. My way of remembering it is imagine the one on the left can be broken in half to make a positive sign, whereas the one on the right can't, so it has to be the negative sign. We talked about voltage drops. That's essentially saying that if voltage is the amount of energy, then that energy gets lost at certain points in the circuit. The main place they get lost at is like light bulbs and buzzers and motors. We don't look at how much gets lost over the wires, even though, and the battery, even though some does get lost over the wires and battery. We just assume that it's zero. And then we can use Ohm's law to calculate bits and pieces. Before we talked about it, we talked about the difference between a series and a parallel circuit. Series circuit being one after the other, just like how you would watch a TV series, whereas parallel, there are multiple parallel parts. They're in line. We talked about then we said, well, parallel circuits are brighter. Why? The reason they're brighter is because the voltage gets, if you've got a 9-volt battery here, then you'll have 9 volts get dropped here and 9 volts get dropped here. Whereas if you have a 9-volt battery here, 4.5 is going to get dropped here and 4.5 is going to be dropped here. And that's because the voltage is shared. Here, the voltage isn't shared, but the current gets split. You actually split the current in half. And then we spent the very end of the lesson saying the order doesn't matter. It doesn't matter which one comes first. This is not the way that electrons work. How electrons work is they think, hey, I've got to get over 2 hurdles, so I'm going to pace myself. I'm going to use the right amount of energy. You might think to yourself, oh, well, how does the electron know how much energy to give to each resistor? It's not like the electrons have brains. And I'd be like, yeah, you're right. The electrons don't have brains. But if you drop, if you have like something like this, right? If you have a shelf, the shelf's like this, and you've got the ground here, and you drop a ball. The ball doesn't know exactly how much energy it has to use before it hits this fence, and then how much energy it has to use before it gets to the ground. It just does it. That's what it does. It just does it. It just uses the minimum amount of energy it needs to use, and that's exactly what the electrons do. And then we talked about if you do use more voltage, the only difference is that you will do it faster. You have a higher current. And then what we did was we got you guys to do this question, which was the homework, not the attendance question. Okay, now today is what we're going to do is we're going to talk about electrical circuits. Now, when we talk about electrical circuits, we're going to talk about it in all of the bits and pieces of them. And I guess the first thing we need to talk about that I want to talk to you guys about is this. I want to talk to you guys about this idea of taking the path of least resistance. There's actually no pencil here, so I don't necessarily want you guys to copy this down. But this is actually to start you guys thinking about a situation like this. Let's say I've got a parallel circuit. Let's draw a parallel circuit. And I've got a resistor up here, and I've got a resistor down here. And what we'll do is I'll put a battery in. Oops. I'm actually going to draw the battery like this. And I've got 2 paths for the electrons to go down. The electrons can go, oopsies. No, what happened there? The electrons can either go down path A and then back out to the battery, or they can go down path B, which is going to look like this one. And what we've been doing so far is we've been saying that these 2 paths are the same. But what if they're not? What happens in the situation where you don't have 2 paths that are the same? What would happen if I said that this path here, this is a 100 ohm resistor. And whereas this one, this is a 1 ohm resistor. So this is really hard to get through because it's got a lot of resistance. It really hampers the electrons. Whereas this one's easy. What's going to happen in this circuit? Well, I want to show you guys a bit of an analogy that I like to attach to this idea here. It will hopefully help explain what will happen here. Because ultimately, circuits aren't necessarily always nice and they're all with the same resistance. And to do that, I like to use something called the mountain analogy. What my mountain analogy is going to look like is this. We're going to draw a mountain in. Okay, we're going to draw a mountain. We're going to make it like this. We're going to actually draw a it looks mountain-ish. And we've got this massive mountain here, right? And what we're going to do is we're going to take a bunch of students. We're going to put all these students over here. And we're going to tell them, hey, guess what? On the other side of this mountain, there is an ice cream shop. And guess what? That ice cream shop for today only is going to offer free ice cream to the first, I don't know, 50 people that come and get ice cream. So if I was them, I'd be like, hell yeah, I want to get to this ice cream shop. And you know, just like that, you guys, we want to get to the ice cream shop. But what we're going to do is we're going to add a little bit of, we're going to put this massive mountain in the way. Now, let's say that we've got a situation here. These students could actually get to the ice cream shop in two ways. What we could do is we could say that these students could make their way and climb over this really, really, really high mountain to get to the ice cream shop. Yeah, sure, easy, right? Or you know what? Instead of going over this treacherous mountain track, we could actually put in, you could instead go, you could instead go up this, you know, this nice and easy path that goes around the mountain. And so the question becomes, which way are the students going to go? Are they going to go over this treacherous mountainous path, or are they going to go, you know, are they going to go over the nice and easy path that goes, you know, around the front of the mountain? What do you guys, honestly, what do you guys think is going to be the way that these people are going to go? Yeah, most of them say, yeah, they're going to walk around, okay? Most people are going to walk around the mountain, okay? Because this path is so easy to walk down. Whereas this path up around the mountain is very difficult. Don't get me wrong, there is going to be some crazy, maybe one, maybe two crazy students that say, you know what, I'm going to go over the mountain because that looks like a better way to go. But most people are going to go, you know, via this path. And that's because they will usually want to take something called the path of least resistance. What does that mean? That means that you want to take the path that is the easiest for you to go down, the path that gives you the least resistance. One of these paths has a huge amount of resistance. This has got lots of resistance. It's really trying to stop people from climbing it. Lots of resistance. Whereas this one is easy in comparison. So what I want you guys to look at now is I'd like you to look at the amount of people. More people are going this way. Lots of people, whereas only a few people are going this way. So how does this translate to this circuit? Well, if you've got one path that's got really, really high resistance, that's exactly like your mountain. And if you then say, well, how many electrons are going to go via this path that's got huge resistance? Guess what? The answer is going to be very few. You might have 0.01 amps. Whereas if you look at how many electrons are going over this path, the path that's easy, the path with low resistance, that's going to be a large number. This might be like 10 amps or something. More electrons are going to go via this path than this path. That's not to say there won't be 1 or 2 electrons that decide to go down the hard path, but it's going to be very, very few. And that's something that I want you guys to think about, right? Now, we know that already, that even though that the electrons will go over this both paths, they'll still lose the same amount of voltage. They'll still lose 10. This is a 12-volt battery. They'll still lose 12 volts here or here, but it just means that the way that they split will be different, not all of them. So that's what we call the path of least resistance. Now, this actually does have some implications for making a circuit. What I'm going to show you guys is, and this is actually a mistake that I see some students make all the time, even students in year 11 physics, even students in, that do engineering maths still make this mistake. And it's to set up a circuit that is called a short circuit. What is a short circuit? A short circuit is when more current will pass through the path of least resistance. What is a short circuit? This is when one path has almost no resistance. What does that look like? And I'd like you to copy this down in this row. So how this looks like is this. You have, let's just say you've got a battery. And let's just say this battery is hooked up to a resistor. And then you got this extra wire that's hooked up like this. People make this mistake all the time. They're like, oh, I'm just going to connect these because I need to connect the positive and negative. And they don't realize they've created a short circuit. Let's say this resistor is like 10 ohms. So how does a short circuit work? Well, the current comes out of the battery. Let's just say we'll do the current in red. We'll say this is a normal amount. We'll say this is a normal amount of current here. And so the current can go, do I want to go down? Let's say this is a 6-volt battery. We'll say, does the current want to go down through the resistor, or does it want to take this path? Look at this path. This path hasn't got any resistance at all. 99.99% of the electrons are going to go down this path here, with maybe one electron every so often going down that path in the middle. This means that there is going to be a large current through this wire. That's fine. Having a large current through a wire, that's not that bad. But what is bad about having a large current in the wire is there's no way, there is no resistance, there's no resistor to give up voltage. So unlike this resistor, which is going to lose 6 volts, you have to drop your 6 volts as you go via this wire. What that means, and that has some pretty big implications, what that means is that this wire is going to lose energy. It's going to lose energy as heat, and that can cause a fire to occur. And that's why you need to be careful when you're wiring things and when you're playing around with electronics, because sometimes you can create a short circuit without even knowing. Sometimes you can create a short circuit by just accidentally putting your screwdriver across 2 terminals. If you put your screwdriver really close to the battery and connect it like that, you've got yourself a short circuit. And that screwdriver will get very, very hot, It may even start making some sparks as the electrons want to go, because the electrons want to go via that, and so then you can actually get a short circuit. So let's talk about it. What I want you guys to write down, I'd like you to draw these pictures as well if you could. But yeah, more current will pass through the path of least resistance. That's a path, one path that has almost no resistance. What happens is you get a large current, there's no resistance to give up the voltage, so you'll lose the energy as heat. That might be okay if you're trying to lose your energy as heat. If you've got like a heater, you could put up a really high resistance wire and then this would work fine. But if you're trying to power up a music stereo, or you're trying to power up a light bulb, this is not what you want going on. So this is sort of linked to that idea. What does a short circuit look like? What could you see what a short circuit looks like? I want to show you guys this here. This is sort of, if I can, yeah. Oh, oops, hold on. I'm not sure if I'm sharing this anymore. Sorry, give me a sec. And I want to share this slide here for a fraction of a second. So this, I'm actually going to cut the audio because the audio doesn't matter too much. Well, actually, no, I'm gonna jump ahead to the one that I care about, which is the best one. In my opinion, this is some dangerous short circuits, but the best one that I think is this one here. Now, what I want you guys to look at is this. So here we've got two high voltage wires. Okay, imagine that this wire here has got a huge positive charge, and this wire here has got a huge negative charge. And so what will happen is that the whole point of this wire is these wires is that they're designed to go into your house, go through your TV and whatever, and then go through. So that would be a high level of resistance. But now what's happened is a stick has formed the wire. This stick is providing a short circuit, a path for the electrons. The electrons can go, do you want to go, the current goes, do you want to go through this house, or do you instead want to take a shortcut and just go through this stick? Or believe it or not, the electrons are going to want to take the shortcut through the stick. So how does this, what does that mean for this circuit? Well, we're going to see right now what that's going to mean. As you can see, we've got this stick is getting very, very hot. It's the only way it can lose all that voltage is in the form of heat. But eventually that stick's going to give way. And that's what happens. At the very end, that stick burns and it completely disintegrates. But when it does that, some of these electrons are already halfway across. So they're going to start jumping to the other wire, but not through the stick anymore, through the air. What it does is it actually vaporizes the air and turns the air into a plasma, a super hot, and a plasma is a super hot state of matter, which has got like electrons that are all flying around and doing their own thing. So now these electrons are like, sweet, I've got a way to get to the other side. I'm just going to go through that plasma. Eventually that plasma gets, because hot air rises, the plasma gets further and further up, and then eventually it goes out because, you know, it's too high, it's too difficult, you might as well just go through the house. But yeah, that's what can happen. And there are other examples. This one is another example of the same thing happening, but a lot faster. Instead, the stick just falls on the wire, and yeah, that keeps going for a while. And of course, the last example is actually just a tree falling down and knocking out some power lines, which is another short circuit. But yeah, this looks really dangerous. We're not going to talk about them too much. I just wanted to show you that. Okay, let's jump back to the lesson. So yeah, here we go. So that's what a short circuit is. It's a parallel circuit where one of the lines that's parallel happens to have barely any resistance. So in our picture, in the video that we just saw, the 10 ohm resistor is just, whoopsies, wrong one. The 10 ohm resistor is replaced by the house. So if I rub out that 10 ohm resistor, and if I put in a house, that's what we're doing. And so instead of going through the house, it's going to go through this stick. So that's what a short circuit is. What we're going to finish up, well, we've got about 5 minutes left, so I'm going to try and get through this last slide, and I think that's going to be it for this lesson. The last slide here is then to talk about, well, we're going to look at, in a series and a parallel circuit, I want to be able to do some calculations. These calculations that I want to be able to do is, all right, so we know there is, so if I know there is a lower resistance, if I know that the resistance changes, if I know all these things, can I calculate them? Is there a way to calculate them? And the answer is yes, there is a way to calculate the resistance. We're going to look for first a series circuit. In a series circuit, what you have is you have your current, I total. Now your total current is going to equal the current, your total current, or IT, or whatever you want to refer to it as, is the same through the whole circuit. Think about it with a series circuit, yeah? If I draw a series circuit here, we'll go with one resistor here, one resistor here, one resistance here. If your current through the circuit is going to be the same here as it is here, as it is here, as it is here, because there's nowhere for the current to go aside from around in a circle. That's why your current is the same at all points. Your total resistance, now this is actually a nice and easy formula that you can do. Your total resistance is the sum of each of your resistors. What do I mean by that? I mean that, let's just say this is a 3 ohm resistor, this is a 4 ohm resistor, and this is a 5 ohm resistor. Your total resistance is just 3 plus 4 plus 5. 3 plus 4 plus 5 is 12 ohms. Your total resistance is 12 ohms. You're just going through the circuit. It's like just imagine that you have a giant 12 ohm resistor. It's the same thing. Your total voltage is the sum of all of your voltage drops. Let me show you what that is. Let's say that you, let's just say you use up 3 volts here, you use up 4 volts here, and you use up 5 volts here. Then that means your total voltage is 3 plus 4 plus 5 equals 12 volts. So that's going to be your total voltage, the voltage of your battery. You can actually use this to your advantage, right? So if I say, if I had a different circuit, let me rub this out. Let me do a different circuit up here. Let's say you've got a 9-volt circuit and you've got that connected to 2 resistors. And let's say this resistor here, you lose 3 volts. You can figure out how much resistance, how much voltage you're going to lose through that resistor. If this one's losing 3 volts, then this one has to lose 6 volts, because if you add up all the voltages, they have to equal 9. And then what you could do is you could play around and you could figure out what the resistance of that circuit is, and so on and so forth. But those are the basic rules for a series circuit. For a parallel circuit, they're a bit more challenging. For a parallel circuit, I'm going to write them down now. the current in each branch. Have I got any time left? I've got about 2 minutes left, so I'm going to try and get through the whole slide here. The current in each branch adds to the total current. That means that if you've got I1, I2, let's just say we'll call this I3, I1 plus I2 equals I3. If you know that the current, and the example that we'll do for a parallel circuit is if you know that the current, here, let's say the current of the here at the start, let's say the current here is 2 amps, the current here is 3 amps, then you know that the total current is going to be 5 amps. Or the total current going in is 5 amps and it gets split into 2 amps and 3 amps. That's what that rule means. The current in each branch adds to the total current. If you take up each branch. If you have 3 branches, then they would add to the whole thing. So that's the parallel one. The resistance is a bit weird. We're going to talk about the resistance. We're actually going to do some calculations of this on Thursday, but just so that you're aware, the total resistance is not, you can't just add the resistance now. You can't just go, oh, I'll add them together. You actually have to add the reciprocals. You actually have to add 1 over R1, 1 over R2, 1 over R3. And I'll explain how that works tomorrow, but I just wanted to write that down. And the last idea, whoopsies, yeah, the last idea here is this. Each path through the circuit must have a voltage drop equal to the voltage.
So does the bell go at 11:48?
Yes.
Oh, okay.
Going in like 1 minute. Hence why this is the last slide I'm talking about.
Wait, on my time it's 11:50.
Okay, well, yeah, that's fine. I may have gone a little bit over, but I'm finishing up right now, so don't stress. So yeah, I'm finishing up as we speak. The last bit here is the voltage drop. We already talked about that. We said if you're dropping, if you've got a 12-volt battery, you're going to drop 12 volts here and 12 volts here. And we've already seen that when we started talking about how these 2 light bulbs will be brighter because they get the full battery voltage. We're going to talk about how that works next lesson. We're actually going to do some calculations on this stuff next lesson. We're actually going to start looking at how you can calculate these for individual circuits. But ladies and gents, that's all the time that I have for you guys today. Thank you guys for listening. Remember tomorrow all the exercises to do, so make sure you get them done by then.